Hi everyone, my name is Justin Lin, and I am currently a senior at the North Carolina Central University. And this summer, I attended the REU program at the Pennsylvania State University, where I worked with Benton Bickerton and Dr. Elizabeth Alakwa on the synthesis and ring opening metathesis polymerization of the Isopentoxy methoxy Paracylophanediene. So, conjugated donor-acceptor polymers are long chains of electron donor units and electron acceptor units covalently linked together. Now, this selective linkage of donor and acceptor units allows for sequence definition, tailored solid-state packing, and tunable band gaps. This allows for interesting optical and electronic properties, which makes these conjugated donor-acceptor polymers attractive for applications in organic electronics, such as organic solar cells and organic field effect transistors. However, there is limited synthetic methodology for achieving these sequence-defined conjugated donor-acceptor polymers. So, one method we use is iterative synthesis. And in this example here, you can see that we have a phosphonate group which couples with an aldehyde, and then that nitrile group reduces to a phosphonate, and this allows for propagation of the polymer chain. So this synthesis method gives us oligomers. It's time consuming and it's not very cost efficient. So another method used is through bi-arrow monomer cross-coupling. And with this method, we can take the bi-arrow monomer and have it undergo commodic catalyst transfer polycondensation to afford us our polymer chains. So this method does give us good control over the molecular weight and dispersity. However, it has limited functional group tolerance. So the method we're interested in was ring opening metathesis polymerization, or ROMP. And in this method, we use a Grubbs catalyst with the ruthenium metal center, and we have it undergo coordination with our Paracylophanediene, and then it undergoes 2+2 cycloaddition to break open that cyclic olefin, and then it undergoes propagation to afford us our polymer chain. So, in the previous work done by Dr. Elizabeth Alakwa, she demonstrated that ring opening metathesis polymerization on her MEH-BT ring demonstrates precise sequence definition. It was electronically and sterically directed. It demonstrated living polymerization, which gives us control over the molecular weight and dispersity. So, my question was, how does steric oak impact ring opening metathesis polymerization? So here you can see that on my isopentoxy methoxy Paracylophanediene, I have a isopentoxy chain, which is less bulky than the chain on Dr. Alakwa's MEH-BT Paracylophanediene. So how does ROMP on the isopentoxy methoxy Paracylophanediene compare to ROMP on the MEH-BT Paracylophanediene? So my first step was to take the isopentoxy methoxy monomer and run it through this 8-step synthesis to afford me 2 isomers of my isopentoxy methoxy Paracylophanediene. And overall, I was able to isolate the 2 isomers, and we ran both isomers through a silica column for purification. And to analyze our 2 monomers, we ran proton NMR. And in our first proton NMR, you can see at 5 and 6, we have 2 peaks which are attributed to the protons in our aromatic ring. And at about 3.8, we have a peak which is associated with that methyl group adjacent to the oxygen, And at about 3 and 3.2, we have these two peaks, which are attributed to the methylene group adjacent to that oxygen. And in our second proton NMR, you can see that we still have our two peaks at 5 and 6 attributed to the protons in the aromatic ring. And now, at 3.8, we have the peak associated with the protons from the methylene group adjacent to the oxygen now shifted downfield, as it is further back and further away from the BT ring and is now being is not being shielded as much by it. And here at 3, our peak associated with the methyl group adjacent to the oxygen has now shifted upfield as it is closer to the BT ring and is now being shielded by it more. So our proton NMR gave us good indication that we were able to synthesize our two isomers of the isopentoxy methoxy paracyclophanediene. However, it did also show that we still have some impurities left in our samples. So my next step would have been to run each isomer through another silica column for further purification. After that, I would conduct an initiator screening where I test the polymerization of my paracyclophanediene with different generations of the Grubbs catalyst to see which one gives me better polymer conversion while maintaining a narrow dispersity. And after that, I would select the most optimal Grubbs catalyst, and I would begin polymerization of the isopentoxy methoxy paracyclophanediene while targeting polymers of specific molecular weights.